So this is third lecture for week 7. What we are going to have a look at is basically a programming paradigm, a way to solve problems. This is a very common paradigm that you'll have to use many a times. That programming paradigm is recursion, and with recursion we'll also have a look at another concept. Again, it's not really a programming concept; it's more of a problem-solving concept, but many a times recursion is used to implement algorithms which are based on that particular approach. So we'll just have a look at them together. So first, let's just a simple recap of what we have done till now as far as iteration is concerned. So you already know how to solve the problem with the help of loops, right? So the idea is that whatever repeated computation you are supposed to do, you are expected to express them in terms of certain variables, and then figure out, in each yeah, at each step, in each iteration of the loop, how exactly do these variables change, and you also need to figure out a way in which the loop basically ends when the problem has been solved, right? So this is a slide from the previous lectures. We have seen this before. Yeah, you initialize some variables. These are the statements which use those variables on which the loop's body is dependent upon, and then you update those values by some amount, and then you check if a particular condition is true or not. And this is one of the ways to uh, to visualize how a loop is written. Now, if you have figured out all these things, you can certainly write loops to solve your problem. Now, we saw one particular example, the example of factorial, via so many different fashions. We used actually the three loops, while, do, while, and for. We used all these loops to solve the same problem, factorial calculation. So we'll actually use that again now with another approach. So the whole idea of recursion, okay, so recursion is a programming concept where a function calls itself, okay, to solve a specific problem. So don't just get confused at this point of time. Some recursion might be a difficult concept to grasp in the first iteration. So just look at the examples that we'll talk about, and then you'll understand what I mean when I say a function calls itself and why is it calling itself. But in any case, in case a function does not actually call itself, but it calls another function which in turn calls the first function back, that too is known as recursion. And you can now understand that there is a kind of chain that is happening, right? Some kind of A calls B, B calls C, C calls A kind of thing, right? So there can be any number of functions in the chain, not just two. The case where a function is calling itself in the body is known as direct recursion, and when there is some kind of a chain via multiple functions, we call it indirect recursion. So this is an example of direct recursion. You have this function f, and at some point of time in this whole function, f is calling itself again. Now it might seem quite idiotic to do it at this step, because why would you call yourself? It might go into a kind of infinite loop, but that is usually not how we do it. It is just to show you that what it means, right? So there is a function f, and somewhere in the body there might be some if conditions and everything here. You call f again from f. So this is known as direct recursion. Indirect recursion with two functions looks something like this. There is a function f, and then it's a function g, and f calls g, and then g calls f back again, right? Again, it might not make any sense to you as of now, like why is g calling f back? But yeah, there are certain cases when it happens. Now the third case is where I am having a chain of three functions. So f calls g calls h, and then h calls f back, right? So the idea is something like this. So recursion is, you can already see that it is kind of a it is kind of a loop, but instead of writing a for or a do while loop, the loops are becoming kind of implicit, because you call a function and then the same function calls itself again. So there is a kind of loop in the control. So this particular fashion of calling itself is a very common way in which people solve problems, especially difficult problems. The first solution that we try to come up with is usually a recursive solution. So you try to express the problem in a recursive fashion. So a very good example of what this recursive formulations mean is the principle of mathematical induction, or PMI, that you might have already studied in 10 plus 2, right? So there what you used to do, you used to prove that a particular premise is true for all the natural numbers, right? 0, 1, 2 and so on. And how do you used to do that? So basically you say that Pn holds can actually be shown if there is some, it holds for the base case, that is 0. Okay, so you basically somehow show that P0 is true, and then you assume that for some natural number k, Pk is true, and then if you can somehow display, if you can somehow show or prove that Pk plus 1 is also true, then you are done, right? So this is how principle of mathematical induction helps us in proving a premise for all natural numbers. So PMI is basically an example of a simple and a very powerful problem solving technique called divide and conquer. Okay, so what exactly is divide and conquer? The core idea of divide and conquer approach is that whenever I have a problem, the idea is that I divide it into one or more smaller sub problems, and then I solve those sub problems, and at the end of, when all the sub problems have been solved, I just construct a solution for the larger problem. Don't worry, you'll get to understand what these things mean as we see some examples. We'll have two examples coming up, but this is the overall idea, that you start with a base case. Okay, so in PMI's case, the base case was P0, right? So you basically say for what how would this problem be solved for a base case, right? So for a very simple input, what should be the output of your algorithm, right? So these cases are usually trivial in the sense that it's a no-brainer. You can simply tell someone, okay, if this is the input, this is the output, that kind of stuff, right? So there is really no algorithm. It's like straight away answer. So we start by seeing that what is the trivial case for the what is the base case for this particular problem, and then we basically see if I have a problem of of a certain size, right? So let us say if my problem size is n. You'll understand what I mean by problem size when we go to the end of this lecture. But the idea is that I have a large problem. Let us say its size somehow measured is n. So you try to find out sub problems of size that are less than n, then you try to solve them and somehow construct the solution for size n. This is the overall broad idea of how divide and conquer works. In terms of programming, the most natural way to code divide and conquer approach is recursion, right? So why? Because you basically say that there is a function f, let us say, and I have some input for this particular function. Now this function simply says, okay, in order to construct a solution for, let us say, an input of size n, why don't I try to first solve the problem at some other level, right? So let us say I try to solve the problem for an input size m, where m is strictly less than n, right? And then once I have the solution for m, I know how to construct the solution for n. So this is the idea, that I repeatedly invoke the function till I reach a level where the solution is trivial, where it can simply be, right, where it is like an input output pair. If you tell me this is the input, and I can tell you what is the output, and then from there onwards I simply start constructing in a bottom up fashion the solution to the problem. So this is the first example. We are back to factorials again. So now, of course, that we have studied functions very well. So now you can see that I have created a function here to calculate factorial. It takes an input, an integer to be precise, and returns its factorial. Now this is more of a convention that I have put in the program, that if you give me a negative number, although you'll see at the bottom the code will not allow you to do that, but still, right, I mean, just for the sake of a little more completeness, I have put this if condition, but it is not really that important. It basically says that if the number is negative, factorial is not defined for you. So this is really some validation and not the actual factorial calculation. This is from where your factorial calculation part starts. You say that by convention factorial 0 is 1, and you also know that factorial of 1 is also 1, right? Because 1, this is how factorial is defined, that for a for a number n, the factorial is defined by saying n into n minus 1 into n minus 2 up to 1, right? So if you want to say what is factorial 1, it is 1 only. So this is in some ways the base case here, that if the number that is given to me to calculate is just 1 or 0, the answer straight away, the answer is 1. Now for all the other cases, okay, if I have a number that is not 1, you can actually see that what I am trying to do here, I am simply saying that factorial of a number can actually be calculated by number multiplied by factorial of number minus 1. Okay, this is the core idea of divide and conquer here, right? That I'm just going to recursively, this is the term that we use, that I'm going to recursively call the factorial function for a smaller number, and then whatever is the factorial for that smaller number, I'll multiply it with the current number, and then I get the answer. And this is exactly how we have studied it in mathematics as well, right? That factorial of n equals n into factorial of n minus 1. So this is very important. What we have just done is a kind of recursive solution to the factorial calculation problem. So just run this code in your head for a few times and convince yourself that we are not going to go into any kind of funny scenarios where I multiply somehow this number by a negative number. It will not happen. That is what I'm trying to say. So just have a look like what happens. As long as you get a valid input, you should get a valid output from this function. And so this is the overall idea. You have to understand that what really we did here. We solved some smaller problem. This is the part where we are solving a smaller problem, and then we are combining the solution of the smaller problem with something at this particular level, and this is the number, and we combine these solutions appropriately, and then we find the overall solution. So this is the overall idea. It is similar to unraveling a series in mathematics, that 1 plus something, right? And then what is that something? You say, okay, that something itself is x plus something, and then you say that the second something is y plus something. So now you are basically coming up with the series which is 1 plus x plus y plus so on and so forth, right? So and assuming that this something is going to go to 0, or some or that this continuation is only going to go up to a certain number of terms, you can say that this is how the series looks like. So it is something similar to like that this whole expression will essentially unravel as number into number n, number into number minus 1 into factorial n minus 2, then factorial n minus 2 itself will become number n minus 2 into n minus 3, so on and so forth. So essentially this expression itself will finally have your whole factorial. So and this is the whole idea of divide and conquer. Now another example that we have is that of binary search. We didn't actually write code for it. We just discuss, and I think I gave it as a homework. So some of you may have written code for it. But here is the code in the recursive fashion. Okay. So there is a function again here. It's called binary search, and what it takes is it. And now this is something that you have to understand, that it is actually taking it is supposed to search for a particular element in not the whole of the array, but basically a part of that array. And you'll understand why does it take this beginning and so this beg and end are basically beginning and end. So what we are trying to say is this function expects these inputs, that you have given a sorted array to the function. There is a beginning index and there is an ending index, right? So let us say the array consists of 10 elements. So the maximum value of end is 9 and the minimum value of beg is 0. So every time we call this function, they'll be somewhere in between, right? So basically you might say beg is 0 and end is 5, or beg is 5 and end is 9, something like that. So in that case, the function is only going to search, only going to perform a binary search in that part of the array, not the whole array, right? So this is, and you'll understand why we are giving these inputs to the function, because this is how divide and conquer approach will try to solve it. And then the fourth element is the value that you want to search in the array. Now if the value is found in that particular part of the array, you simply return the index at which it was found. Otherwise you return -1, right? So it's again a kind of convention that I'm using, that -1 essentially means that the value is not there at all in this array. So this is how the code actually works. If the beginning index is greater than the ending index, right? So let us say uh, the beginning index is 5 and the ending index is 4. It means that the size of this array part is 0, right? I mean there's just no element in this part of the array, and if you have no element, then there is nothing that you can search, right? A 0 element array does not contain anything. So now the key becomes irrelevant, right? You are simply going to return -1, because there is no way you can find something in a 0 sized array. Then what we are trying to do is, if you remember in binary search, I told you that the best place to look up, best place to look up in the first iteration is to look up at the midpoint of the array, and then you decide whether I should look at the left part or the right part based on the comparison between the key and the value at the midpoint. So this is where we are going with this, that we try to find the midpoint of that part of the array, and then we check if that particular midpoint, that index, contains the key. If it contains the key, then we simply declare yes, we have found it, and this is this is what I'm doing. I'm returning the index mid. It means that I have found the value key at index mid. If I do not find it at that particular index, then you all know that what binary search tells you, that it says that then try to compare the key with the value at the midpoint. If this value is less than the key, then you know that if at all the value exists in the array, it will be in the right part, okay, because it is a sorted array. So essentially what I'm trying to do here is, I actually recursively call the binary search function, but this time the value for beg is changed from whatever it was earlier to mid plus 1. Why mid plus 1? Because I have checked up to mid, right? And the key is greater than the point at mid. So now all I have to do is I have to check from mid plus 1 to the rest of the array part, and because if at all the key is present, it will be in that part of the array. We have discussed this already. Similarly, the opposite case is, if the key is smaller than the midpoint, then the element at the midpoint, then all I have to do is look into the left part of this part of the array, and so I pass end's value as mid -1. So this is, I mean, I think you guys already understand it, because we understand how binary search works. So now the overall idea here is that we call this particular function with the array where we want to search. Of course the array has to be sorted, and this is 0, in the beginning, because I want to search it in the whole array. I say beg equal to 0 and end equal to 9. This is the 10, this is an array of size 10. Okay, so I pass 0 and 9 as the values for beg and end, and then I give a key. So this essentially means please binary search for this key in this array, this whole array. And then right, so this is another divide and conquer example. So just again, make sure that you understand how this is going to work. This is slightly more complicated as compared to the factorial function, because in factorial, and let us just compare them together, that basically in factorial, at each step we reduced the size of the problem by 1, right? Because if I am supposed to find the factorial of n, what I am doing is I am saying, okay, let me somehow find the factorial of n minus 1, and if I have the factorial of n minus 1, I will multiply it with n and I have the answer, right? And how do I find the factorial of n minus 1? I call the factorial function again, okay, with the reduced value. So in factorial, what I am trying to do is I am reducing the size of my problem by 1 at each stage, and I know that as soon as the problem reaches the value 1, I am simply returning 1 from there, right? So then it will backtrack, right? Backtrack, and all the values are going to get filled up in that series, and I'll finally have the factorial. In binary search, at each step I'm actually reducing the problem size by roughly half. When I say problem size, what I really mean is, if I had an array of size 10, then maybe the midpoint in the beginning would have been 5 or 4 or 6, whichever way you do integer division or floor or seal, whatever you use. But basically you will probably look at either index 4, index 5 or index 6, and then based on that, in the next iteration, I just say, not iteration, in the next step of the algorithm, I discard roughly half of the array. Why? Because based on what is the value of my of the element at the midpoint, I can be sure that the key could either be on the left or on the right. So I can actually discard at each step. I can actually discard half of the part of the array that I was looking for. So at each step I actually reduce the size of my problem by roughly half, and at each step in factorial, the solution to the larger problem is either trivial. So trivial as in, if the number is 0 or 1, I simply return 1, or 1 from the function. So because that is by convention, or the solution can be found by combining the solution of a smaller subproblem with a trivial element. So in this case, the trivial element was the number itself. So you simply say number multiplied by factorial n minus 1 is the solution, right? So what I just did, number was a trivial element that I combined with the solution of the sub problem, and I have the solution to the complete problem. In binary search, at each step, what I did was, I divided. I had two possible ways to go, right? I can either go to the left side of the array or the right side of the array, and I said that whatever is the solution of either of these two problems, whichever one I am picking, that is also the solution to the larger problem, right? Because this is what I was saying, that in the beginning I said the key can be anywhere from index 0 to 9. Then I say, okay, the key can be anywhere from 0 to 3, or 5 to 9, or and then I say the key can be anywhere from 1 to 2, something like this, right? So essentially at each step I keep on reducing the size of the array where there is a possibility to find the key, and at one particular stage, when I keep shrinking the array parts, at one point of time I'll reach at a place where either I'll find the number when the array size, when the midpoint is the place where I find the key, or I would have exhausted the array itself, right? Because the part of the array to search for has become 0, at which point I can simply say that the element is not there. So we know that we have the final solution in case of factorial when the base case is found, that is my number is 1 or 0, then I can say, yeah, now the solution is there, and I can simply reconstruct the solution bottom up. In case of the binary search, we know that if either of the two base cases were um, you find the element on the midpoint of the array part, or the array itself has been exhausted, so you don't have any array part left, your array part is of size 0. So if any of these two solutions, if any of these two base cases are found, you say that now I have found the solution. Now this is a slightly more complicated statement. If you don't understand it, it's fine. You'll probably understand these things when you study when you're doing a course on algorithms. But basically, in the case of factorial, I actually need n steps, right? So there will be like n calls to that function of factorial in order to construct the final solution. And here in the binary search case, this is a slightly complicated notation. It basically says ceiling of log n to the base 2. Okay, so what does it mean is something like this. Let us say if you had an array of size 100 to start with, after first first call to binary search, you will probably discard 50 or 51 elements, and you will be left with only 49. Then in the next one you will be left with maybe 24. You keep on halving, you keep on removing half of your array. So from 49 to 24 or something like that, or 12, then 6, then 3, something like this. So if in terms of your mathematics, this is basically the same as finding the log of that number to the base 2. So if I have an array of size 100, 2 to the power 6 is 64 and 2 to the power 7 is 128. So log 100 to the base 2 will be 6 point something, right? And when I say ceiling means I just take the next integer, the smallest integer bigger than this number, so that is 7, right, in this case. So what I'm trying to say is that even in the worst case scenario, you will an array of size 100, it will take only 7 calls to figure out if the number is there or not, right? That is kind of the worst case scenario. But don't worry much about it. You'll understand more when you study algorithms. There is some homework. We'll discuss it on Wednesday, this lecture. Bye.